Greetings, I'm Kshiteej Mahajan. I'm a sixth year PhD student at University of Wisconsin-Madison. We have an interesting lineup of papers on cloud computing at ATC this year. In this presentation, I'll introduce you to several topics in cloud computing and give you a quick overview of all these papers. Here's the agenda for my talk. I'll first give an overview on several topics in cloud computing, and then I'll give a quick preview of all the papers. Let's jump into the overview. This slide denotes the typical use case of cloud computing for data analytics. Applications use the cloud to store, serve, and analyze several datasets. These applications are powered by a stack of services as shown in this figure. At the top of the stack, we have apps that want to crunch some data in the cloud. Below the application layer, we have several layers comprising of the platform layer, the runtime layer, and the resources layers that are packaged as different service offerings that power these applications. Now I'll take you down the stack to explain the different layers of the stack and explain the interfaces between these layers. I'll give a quick overview with a simple example. Let's take an application that wants to analyze a weather database and wants to find, say, the coldest city in Wisconsin. The application uses a platform like SparkSQL to do this. The application will use the programming abstractions or the APIs exposed by the platform to express this computation, and in this case it is expressed as a SQL query. The SparkSQL platform then takes this SQL query and compiles this query to a data flow that can be thought of as a directed acyclic graph, that is, a DAG of operations. In this case, the DAG consists of two operations, an inner join operation on the input datasets and a sort operation on the output of the inner join operation. Apart from compilation, SparkSQL platform is also responsible for execution of this DAG of operations. To do so, the platform submits each operation whenever its input are ready as a task to the runtime. The platform is also responsible for fault tolerance and managing any intermediate state such as the output of the inner join. The tasks are executed in the runtime as shown in this figure. In this example, the runtime is the Linux guest operating system running on several virtual machines leased from a cloud provider. In summary, the application layer uses the programming abstractions exposed by the platform to express computation. The platform layer compiles the computation as a data flow of tasks and manages the execution of tasks and any intermediate state in this data flow. And the runtime layer is responsible for fast and secure execution of these tasks submitted by the platform. There is active research happening as well as development in industry across these different layers of the stack, and the stack is constantly evolving. Let's look at each layer one by one and look at how these layers are evolving. At the application layer, the key question is, how are use cases and datasets evolving? Datasets and use cases are evolving, and this slide shows a few examples. Datasets can be of various types. It can be structured. An example is a weather database with well-defined tables and schema. And an application or a use case might be to compute, say, the coldest city from this database. Datasets can be unstructured. An example is tweets from Twitter platform. And an application might want to filter tweets by a keyword. Datasets can also be graphs. An example is the internet, where web pages are vertices and hyperlinks are edges between these web pages. And an application might want to rank these web pages by running the PageRank algorithm on this graph. Now, datasets can also be of several modalities. Datasets can be a batch. An example is last year's weather data. This dataset is static and doesn't change, and an application might want to find the lowest temperature on this static dataset. Now, this can be run as a one-time query. On the other hand, dataset can also be a stream. An example is real-time weather data from temperature sensors. This dataset is constantly evolving, and an application might want to keep track of lowest temperature in the last 5 minutes. This cannot be run as a one-time query and needs to be recomputed whenever the dataset changes. At the platform layer, the key question is how to design faster and resource-efficient platforms for new use cases that we just saw. Now this has triggered research and development on several new platforms, and this slide shows examples of several platforms developed for applications on top of different dataset types with different data modalities. At the runtime layer, the key question is how to make runtimes fast, efficient, and secure. This has triggered evolution in runtimes over the years, ranging from virtual machines to containers to serverless functions. This image shows the various layers of the software stack for different runtimes. These runtimes are used by tasks submitted by various platforms. The gray portions are shared across tasks, and the white portions are managed by the platform's tasks. The most recent serverless runtime is known as function as a service. As we can see with serverless, the white portion has shrunk, and the tasks submitted by platform only specify application logic, aka functions. This greatly reduces management overheads, and provisioning of tasks or functions is really fast and of the order of milliseconds. Moreover, the gray portion has enlarged, leading to more sharing across tasks, leading to more resource efficiency, and reducing costs for the cloud provider and the application. Lastly, the resources layer is also evolving as new types of hardware are introduced. Hardware resources in the cloud are evolving with new types of accelerators, more memory, and faster interconnects. Platforms and runtimes must constantly adapt to leverage these advances. These resources are also spreading out geographically to include IoT sensors and edge compute. Again, platform and runtimes must adapt to efficiently scale to these new resources and partition tasks on top of geographically distributed datasets that span the cloud, the edge, and IoT resources. In summary, we have looked at the various reasons contributing to evolution across different layers of the cloud computing stack. This brings me to the excellent lineup of research papers on cloud computing at ATC that advance state-of-the-art at different layers of the stack. The first set of papers in blue proposes faster platforms for emerging class of applications. The second set of papers in green proposes mechanisms for performance debugging of existing platforms and runtimes. And the third set of papers in orange propose mechanisms to make runtimes faster. Let's look at these papers one by one. First, we look at Dart. Dart proposes an edge stream processing engine that processes data generated by geographically distributed IoT sensors. Let's first look at issues with existing platforms for edge stream processing. Existing platforms propose a centralized architecture where any edge processing task is dispatched by a centralized monolithic master with an exponentially increase in IoT app deployments. This leads to queuing of task requests at the master and leads to long tail latencies. Dart overcomes these challenges by using a decentralized architecture. It uses distributed hash table-based peer-to-peer overlay network for deterministically dispatching new or failed tasks across edge resources. Next, we look at two papers that propose memory-efficient platforms for batched graph analytics and streaming graph analytics. To understand the key issues with graph analytics, it is important to understand how graphs are stored and computed upon. Graph vertices are partitioned across a distributed set of machines. Typically, all vertices of the graph first execute some compute function and generate intermediate state in the compute phase. In the aggregation phase, intermediate state is batched and pushed over graph edges that might cross machine boundaries over the network. This leads to two key challenges. First, the size of intermediate state is dynamic and cannot be estimated beforehand. Second, this can lead to uncontrolled memory consumption and can exceed hardware memory limits. The system ADFS overcomes the drawback of existing platforms and operates under strict memory consumption limits. It abstracts batched graph processing as a combination of breadth-first and depth-first style of executing graph processing operations. Breadth-first processing leads to faster performance by executing more compute operations but more intermediate state and hence more memory consumption. Depth-first processing leads to lesser memory consumption by processing intermediate state faster, but it also leads to reduced performance. ADFS, or also known as almost DFS, dynamically switches between breadth first and depth first styles of processing to operate under strict memory limits while giving good performance. Next, let's look at issues with existing platforms for streaming graph analytics. Existing platforms maintain all intermediate state to incrementally recompute over changed portions of the graph. Now, maintaining all intermediate state is memory intensive. The streaming graph analytics paper at ATC controls the memory footprint by proposing two techniques to prune the amount of intermediate state. Next, we move down the stack to look at papers on various aspects of performance debugging. We first look at CrystalPerf, which learns to characterize and estimate performance of data flow computation for different resource configurations. First, we look at issues with existing performance estimation tools. These require intrusive code instrumentation to generate informative low-level traces. This does not generalize to different platforms and requires manual analysis of traces. To overcome this, CrystalPerf is platform agnostic and automated. To do so, CrystalPerf learns performance characterization models by using machine learning. It uses code traces, code documentation, and past execution profiles as a dataset for this learning task. Next, we look at a paper that debugs mysterious slowdown experienced by a large-scale genomics cloud platform. This paper does a non-trivial investigation to find the obscure VM aging problem, wherein VMs get slower with age due to frequent extended page table violations, which trigger a lot of back and forth between the guest OS and host OS, leading to slowdown. Next, we look at Warden, which automates incident detection for the cloud systems. Existing incident detection systems are inaccurate and slow as they apply handcrafted rules on alerts generated by various cloud systems. Warden overcomes this by pruning out noisy alerts and learning machine learning models that associate groups of alerts with potential incidents and automatically notifies the right set of on-call engineers. Next, we move down the layer to look at the series of papers optimizing the runtime layer. First, we look at Parasync, which proposes a scalable scheduler for large production clusters. First, let's look at the issues with existing runtime scheduling architectures. These can be of two types, shared state and two-level. Shared state scheduling architecture exposes all the cluster resources to all the platforms and reactively handles task scheduling conflicts. This is not robust under high task contention scenarios when the number of scheduling conflicts increases. On the other hand, two-level schedulers avoid conflicts and set aside mutually exclusive cluster resource partitions for different platforms. This can lead to unused resources and poor scheduling efficiency. Parasync overcomes these scaling bottlenecks and proposes partitioned synchronization scheduler architecture that optimizes away the bottlenecks in shared state scheduling architecture. Next, we have three papers that look at optimizing serverless runtime layer. Fastnet looks at reducing function provisioning latency and also costs, while Fastlane and USENIX look at reducing function communication latency. Before we look at key ideas of this system, let's look at three main issues with scaling serverless. First, some serverless offerings fetch container images from a centralized registry and experience I/O and network bottlenecks during demand bursts. Second, some serverless offerings fetch container images from a peer-to-peer registry made of dedicated high-performance root nodes. These root nodes are expensive, which leads to increased costs. Third, existing serverless offerings communicate across functions via object storage or distributed shared memory or globally visible message queues. These mechanisms cross several layers of the software stack as well as the network in some cases, leading to high interaction latency. To make matters worse, existing serverless offerings do not place functions in a communication-aware manner. Now let's look at the key ideas to overcome these issues. Fastnet overcomes high provisioning latency without incurring high costs. Fastnet uses non-overlapping tree overlays over existing VMs in the cluster for distributing container images. Fastlane spawns interacting functions as threads or processes in the same container and uses existing lightweight inter-thread and inter-process communication mechanisms, which leads to reduced function interaction latency. Sonic proposes a scheduler that does communication-aware function placement and dynamically chooses the optimal data passing technique for each function communication. This also leads to reduced function interaction latency. To summarize, I gave you a short preview on interesting set of papers that propose novel optimization straddling different layers of the cloud computing stack. I encourage you to attend these sessions to learn more about these different projects. Thank you.